as this thing decays. Okay. We had talked about what it means when you do the calibration. Now the state of California will allow you to do your own calibration, but you do have to have what they call an NIST traceable source. Okay, and what does NIST stand for down here? Yeah. I don't know why I put down National Institute of Standards and Technology. It should be Science and Technology. But anyway, those sources are very accurate. So whenever they do testing of your dose calibrator or your survey instruments, those sources are traced back to this organization. Remember, it used to be the Bureau of Standards. Okay? So when they talk about you doing the quality control on it, you have to check each one of your levels. For each one of your scales. So remember I told you that what they're basically saying is, what is that? Okay, so when we're talking about any survey meter, then you notice that this one has 3 different scales. There's also a battery check. So every morning when you start your day, or at the end of the day when you do your surveys, or do you do your surveys in the morning before you start, or do you do them in the evening after you're finished?
Before you start.
Huh?
Before you start. Oh, survey, yeah. After for the contamination.
Okay. Well, some people do it before they start, just to make sure that if you have a department where there's more than one person working and you have a late shift, it's probably a good idea to do it every morning before you start. But the thing is, so what you'll have is something like this, and we have 3 different scales. So we measure, okay, here's the middle point here. So I want to get a reading at this point and this point. So that means this is the times 1 scale, so this will be 0.5 MR, and then also 1.5 MR. So that's my first one. Then I would move to the times 10, so that's going to be 5 and 15 MR. Okay, and then the last one down here is times 100, so that would be 50 to 150 MR. Okay. Now, if you guys read that email that I sent, one of the questions is they wanted to know, where do you guys do your surveys? And what they're actually asking for is something that looks like this. Remember this? You guys all have something that looks like this? Do you guys have that you fill out? Now you guys don't have it, don't worry, I'm going to send it to you. Okay, but don't, this is what the whole thing of doing the survey is. You have the data here, you have a diagram of your nuclear medicine department. You identify what all of these things are. And when you get your radiation reading, you mark it down on each one of those points. If there's, now down here I have an action level. Okay. So my background in the nuclear medicine department is about 2 MR per hour or less. Okay. So there's a couple of ways that we look at this thing. If it exceeds 2 MR per hour, then I'm going to have to decontaminate. But these are a list of all the places that I monitor every day. Then over here, this is for my contamination or my wipe tests. So the combination of either the wipe test or the survey meter reading these will determine if you have to do a decontamination. The other thing is down here, if you locate an area that's contaminated, you put down that you did wipe tests until there was no reportable or any counts per minute or DPM. So in other words, you kept doing wipes until you no longer got any removable contamination, and then at that point you covered it with a poly-lined towel or chuck, and you put a radiation warning on it, and you let it decay. That's all you can do. If they want to know what the radionuclide was, you can take one of your wipe tests, and you can put it in a plastic counter, and you can either put it on your gamma camera and look at the spectrum, or if you get creative, you can do a 1-minute count. If the counts are high enough, calculate the decay constant, figure out the half-life, and then that'll tell you what the radionuclide is. Hey! Okay, there's a couple ways you can spin the cap. Okay, so with that being said, okay, one of the other things that I'm going to be sending you are forms that you need to fill out so that you can kind of keep track of this. Okay, we talked a little bit about linearity, so let's just kind of the one that you're going to get the most testing for is going to be the dose calibrator. Okay. And I don't think there's anybody that does self-calibration. They don't normally have this on your board exams. But like I said, on the radioactive material license, if you decide you don't want to send it out to a company that charges you about $200 or $300 to do it for you, then you can show the Department of Health that you do it yourself and that you have these sources here. Okay. And again, I would strongly suggest that it's a lot easier and less time consuming if you have an outside firm do it, because in most cases you're not going to have the time to do this yourselves. And then down here for the dose calibrator, this is the important one. They're probably not going to ask you this, but you do have to have radiopharmaceuticals that are greater than 10 microcuries. And for an accuracy test, I mean, if you are going to be using it, remember that you have to assay it, make sure that it's within plus or minus 10% of the stated activity. If you're at 20% plus or minus, then you're having misadministration. Okay. So the test that we'll talk about, everyone okay with geometry? So everyone's okay with the geometry, making sure that your syringes, your vials, everything are corrected for volumes. Remember I told you, you'll either have a vial, and you may have 1 ml in there with 10 millicuries, and you put it in your dose calibrator. And it should read 10 millicuries, right? Okay, if I keep adding water to this, if I add another ml of just normal saline, what should it read when I put it in the dose calibrator?
Okay, what'd you say again?
Okay, if I add another ml of here, normally you're going to have something that looks, this is what I do, and this is what I'm going to do on your test. Okay, I'm going to give you a graph like this. Okay, and then I'm going to have, okay, so here's 1 ml, 2 ml, 5 ml. So you're going to have a bunch of different ml here, maybe up to, normally for whatever size syringes you use in the department, this is what you're going to have. Okay, and then the activity. Okay, 10 millicuries, 9.9 millicuries, 8.5 millicuries, and 5 millicuries. Okay, so if all I have is 10 millicuries in there, and all I'm doing is just adding saline to get these volumes, okay, remember the reading should be about 10 millicuries. Agree? All of these should be 10 millicuries. The reason these values change is because the detecting area of your dose calibrator is not very large. And what some people think is that you have this big chamber of air that completely surrounds the whole, your whole dose calibrator, but actually you only have like 3 little pockets of air that they use to collect the ions. Okay, so when you put your vial in here, here's your detecting area here, so this is your gas. And as you fill this vial up, you lose more and more photons out the top. So you have to correct for those. Okay, anytime you have more than a 10%, you have to correct for it. So, in that particular case then, we kept on adding volume to this, and these were the measurements that we got. So, one of the things you're going to be asked for is to develop a correction factor. Because once you've determined that you have geometric problems with your dose calibrator, then you have to provide correction factors for it. Okay? So do I need any correction factor for this one?
No.
No. Normally, if there's no correction factor, you just leave it at 1. Okay, what about this one here?
No. Or plus or minus 10%.
Okay, plus or minus 1.
Yeah.
So basically, I would be allowed between 9 and 11, right?
Yeah.
Okay, so I really don't need one for this, but, you know, so we're okay. So what about this next one here?
Yes.
Yes.
Okay, so for a correction factor, remember we put the activity that it should be, and we divide it by the activity that it measures. Okay? So in this case here then, it should be about 1.15, is that right? What's going on with this computer?
1.17 or 1.18.
85 to that is, or 8.5, is what is it, 1.75?
1.17.
Okay. Okay, so that means that the correction factor here, we should have 1.17, so there's about a 17% error. So anytime you have a 5 ml syringe, you have to take the activity and multiply it times the correction factor to get the true activity. Okay? And again, this is where you guys can have a problem, because let's say that you get a dose of MDP, it says it's 20 millicuries when you put it in. It comes in a 5 ml syringe, but you multiply that times the correction factor, and we have a problem. Okay, so do we have a problem? If I go with my 10% rule, I'm allowed 20 plus or minus, so I can have between 18 and 22 millicuries, technically, right? Okay, so this is about 17% too much, so most people would probably just go ahead and inject it. But the thing is, technically, this is incorrect. Okay? This one for the next one is even worse. So you have 10 millicuries divided by 5, so we have a correction factor of 2. So we do the same thing with a 10 ml syringe. Now this is also, of course, assuming that the syringe is full, because if the syringe only has 1 ml in it, it's not a problem. If the syringe has 10 ml in it, then it's a problem. Okay? So here would be our 20 millicuries times a correction factor of 2, so you'd actually be administering 40 millicuries to the patient.
Where's the 20 millicuries come from?
Well, if this was a dose that you received in a 10 ml syringe from the radio pharmacy,
Oh, okay.
or if you prepared it yourself. Okay. So again, the geometry is something that, you know, normally it has to be done when you first get the dose calibrator, and anytime you have any kind of a major repair on it. Okay. The next thing we talked about was the constancy, and what you're going to be getting. Okay. This is actually a miniaturized thing that we use in our nuclear medicine department. But basically over here, this is how you handle the problem of receiving radioactive material and disposing of it as part of your requirements. Because remember, you're supposed to use your survey meter to do this. So what does verified mean over here?
Verified by the tech.
Verify what?
The information is correct.
Up here?
Oh, I thought about the website.
Okay, well up here, so you notice it starts in steps here. So you put the date, survey meter calibration check, so that's the constancy check. I also would put up here a battery check, but you know, I didn't make up this form. So you check your constancy. If it's okay, you check that. You put your initials over here. Verification. Ashley, what do you verify when you guys have done this, right?
The white test and stuff?
No. Well, we're going to start with the verification here. What do you think you need to verify?
It's been done.
The stuff in there, like if it's tech or iodine, xenon.
Yeah, this first thing here is you verify the shipping, what was shipped to you. So if you ordered 3 MDP doses and an indium and an I-123 capsule, you verify that it was good, that you got what you ordered. Because do they think they might make a mistake and accidentally send you the wrong stuff sometimes?
Yeah.
Doesn't happen very often, but it only has to happen once. Okay? So that's what verification means, is that you check what you ordered with what they sent you. Okay, then the wipe survey. Remember, you have to wipe the box. What are the allowable limits? If your box measures, what is it, the 5 by 5? I can't remember what the...
It's 100 square centimeters.
Yeah, most of those cardboard boxes they ship our stuff in, if you measure just the surface, the top, each side is 100 square inches. I want to say it's, is it, I can't remember. Anyway, it works out to be 100 square inches. So what would be the allowable counts per minute on my wipe survey?
25.
Huh?
25.
Well, you're going to be measuring DPM. Okay, that was in the math book, under that section of converting CPM to DPM.
Oh.
Okay? It's 22 counts, or 22 DPM per centimeter squared. Okay, so if I have 100 square centimeters, 100 square centimeters times 22 is 2200 DPM. So if I just wipe the top of the box and put that wipe in my well counter, I should not get any more than 2200 DPM. Okay? But that's assuming that I know the efficiency of my well counter, correct? You guys all know the efficiency of your well counter, correct? I think that might be something, when you guys are rotating through your hospitals, you need to look at this stuff. Unfortunately for you, if the state comes there, they are going to hold you as liable as the technologist. Do you understand that? So part of your orientation as a student is they're supposed to tell you where all this stuff is. Where's their quality control stuff? How do they do it? Because if the state asks you questions, then you're expected to know them. And God forbid anybody who doesn't have their radiation badge with them. You guys don't take them home with you, I hope. You do take them home. Okay, then, after you do the wipe survey, okay, we have the surface and the 1 meter reading of the box. And this should actually be done first, shouldn't it?
Yeah.
Okay, so when you have that box sitting where they normally deliver it, and this stuff is supposed to be delivered to the same place every day, first thing you do is you stand 1 meter back and you survey it. Because if there's any problems with it, you don't want to be turning on that meter while you're standing right next to it and discover there's a leak. Okay? So you measure it at 1 meter, then you measure it at the surface, then you do the wipe test. So you should really kind of do these in a different order. And also here's your background, here's the initials of you who did it. Okay? And then when you send it back and all that good stuff. But we're down here at the dose calibrator. Okay. So up here, here's the channel check. And what we're looking for on this, well, there's 2 things. This is not a daily accuracy check. This is a daily constancy check. So what we're going to do is, remember, we have cobalt, we have the cesium, and we have barium. If you guys use a lot of thallium, then some people have a 198 gold source that they use. Okay? So there's, if you have radiations that are higher than 1 MeV, then you may have a radium source, because they have 1.17. Or you may have a cobalt 60 source. Okay? But in any case, depending upon the energy of the radionuclides that you use in your department, you may have other sources. But these are the big ones here, the cobalt and the cesium. If you have I-131, then you use that one. The theoretical is the expected. Because remember, to calculate precision, it's expected minus actual divided by expected. So if it states that there's 100 or 10 millicuries of 57 cobalt, then that's what you put down here. Okay? And then what you actually measure is here, and then you use that formula to fill this in. Okay.
So that constancy is precision, right?
Yes. Constancy and precision are the same thing. Now in California, the action levels are plus or minus 5%. Because if you have what they call an intra-assay, if you measure the same source over and over again, then there should be less than 5% error. Okay? If you get sources from radio pharmacies like doses for patients, they allow you plus or minus 10%. Okay? So that's why here in California and Maryland it's plus or minus 5%. And there's your initials there. Okay, now the theoretical activity, if you have a really, really nice physicist, okay, he'll give you something that looks like this. If you see, now you probably have a computer that has this information in it. If you don't, it's very easy. You can create a Excel spreadsheet and use that decay formula to decay it down. But the thing is, okay, the initial activity that we had, Cobalt 57, it was manufactured by Nuclear Associate Services. This is my serial number. The activity was 5.05 millicuries. It was calibrated for November 1st of 1998. Okay? So that's my cobalt source. And then over here is my cesium source. Okay? Actually, never mind, that's my dose calibrator. Okay, this is my cesium source over here. So 107.2 microcuries as of the 3rd of December 1987. Wow, man, that's a long time ago. Because here we're looking at June 1st of 2000. So how many years is that?
13.
Huh?
From 2000 from now.
Okay, 13 years, right? So are you guys concerned?
No.
Yeah, because this thing has a 30-year half-life. So I got about another, how many years? Got another 17 years before I even have to worry about this being 50 microcuries. But you notice that they decay it down. So my activity on June 1st should be 1.382 millicuries. This is plus or minus 5% and plus 5%. So this is the number that I would enter into my quality control book, and then when I assay the source, it should be within this range. Okay, so most people just, they do that because it's just a lot easier. So long as it's within that range, we just go on to the next step. Okay. So we have it for both the cobalt, and then over here is the cesium. So as of this date here, we have 80 microcuries after 13 years. So here's my minus 5%, my plus 5%. So long as I'm within this range, I'm good. Okay? You guys have all done this, right? This is one of your competencies. I don't know if you're aware of that. But in your competency book, this has to be signed off that somebody observed you do this. Okay? So that's your daily constancy check. But we're not done yet, because this next one over here, what do you think I'm doing here? Okay, 137 cesium. Okay, here's my measured activity here. Okay. And then over here, I put down my measurement of the cesium source using the different channels on my dose calibrator. Okay? So over here, even though I have a source that says it's, at this point it should be about 80 something microcuries, if I put it in and measure it under the cesium window, it should be 80 microcuries. But under these other windows here, it's going to be different, right? Okay? But it should be consistently different. In other words, if I put it under technetium and it measures 70 microcuries, every day that I measure it, it should measure about 70 microcuries, plus the decay. Does that make sense? Okay. So this is what they call the channel check. Is this required by the NRC?
Yes.
No, it's not required by the NRC, but if, well, people like it when you do more than what you're required to do. So the if you did a channel check, they're very happy with you. Okay. Then, because the state loves us so much, and going back to the California state license thing, the annual accuracy test, your health physicist will come in and he will, measure his NIST sources in your dose calibrator, usually once a year, make sure that those are okay. And then the other thing that we will look at is what we call the linearity. Okay? Now, I told you last week, what are we looking for with linearity? now let me ask you again, have all of you guys done this?
Explain it to me.
What, yeah, what is it?
You guys haven't done linearity?
Is that where you
That's what
look
they're
at?
doing over there.
Oh, yeah.
What do you do?
They told me that next quarter they'll be doing all of that linearity geometry
Where they got
at my
the,
last clinical site.
they got
Are you
the
guys gonna be
source.
there to see it though?
Monica is.
They got the source and they measured it initially and then every 6 hours until
Okay.
it was below a certain amount.
Let me just- Somehow, I think I must have rested my book on the keyboard here, because I've got like 10,000 help and support center things here. I'm down to the last 30 or so here. Let me see if I can spit these out a little here. Okay, basically with linearity, we put Mr. Singh on the spot here. Mr. Singh, what am I looking for with linearity?
You're looking for?
Yeah. And have you guys done it yet?
I've done it once.
Okay, so can you kind of give us an explanation of what you did?
Yes, actually, what they do is that they put a source in the dose calibrator, and they'll count, maybe they'll measure 4 hours later, and for example, if the source is 10 millicurie, and the next 4 hours, the expected number would be maybe 7, and then measure that again, and they'll see if the dose calibrator works properly. If they don't get that expected value, then something's wrong with the dose calibrator. For example, if you measure technetium 99 at 10 millicurie, you start at 10, and then 6 hours later, it should be 5 millicurie, and you measure that again. And if
Well-
you don't have 5 millicurie, then something is wrong with the.
Well, the 10 millicuries is probably not accurate. Because notice what it says up here. For a dose calibrator, it should be ascertained over the entire range of activities employed. So that means if you do nothing but heart, if you work at an imaging office and you do nothing but hearts all day, the maximum activity that you would need for your linearity test is 30 millicuries. If that's the maximum that you inject. If you apply therapy to thyroid cancer patients, then you might want to use 125 millicuries of technetium. So technetium is used for this, and that sounds like a good test question for next week. Okay? So for a linearity test, what you're doing is making sure that your dose calibrator is able to measure high doses, medium doses, and low doses. Because you're going to start with the maximum activity you use in your department, and you're going to decay it down to what activity? You remember how far you decayed it down to, Mr. Singh?
I don't remember exactly, but they did it all day.
They just did it all day? Ashley, you haven't done this yet, have you?
Wait 2 hours later, I think 4 hours later, we measure again, and 4 hours later, we measure again.
Okay, well, again, you need to know when to stop, okay? Typically, we only go down to about 30 microcuries. So however much time it takes for that. One way that they do it is by just, you measure it every 6, 24, 30, and 48 hours. Okay? Or remember, we have these devices called CalCheck, or the lineator, and what they are, they're shielding that you put around your syringe that simulates radioactive decay. In other words, there's a certain number of half-value layers in it, so you can get this thing done in just a few minutes, probably about 15 minutes, as opposed to 48 hours.
You said we go down to a 30 millicuries, what do we start with?
Well, whatever the maximum is that you use in your department. So if you do radiation, if you do iodine therapy treatments at 100 millicuries, then you should have 100 millicuries. What you do is you order 100 millicuries from the radio pharmacy. You don't let anybody touch it, and then you just take it out of the vial and assay it all day long. Or if you have those lineator shields, you put it in there, you measure it, it simulates 6 hours, so you should have half. Then you put another sleeve over it, that'll make it, 12 hours, and then another one. Yeah, so eventually, like I say, in about 15 minutes, you can simulate 48 to 72 hours of decay. Typically for 100 millicuries, it takes about 72 hours to get it down to 30 microcuries. But here's the thing with that. Okay, you will have a plot and here's your time and here's your activity. So if you have 100 millicuries that you start with, okay, you've got 6, 12, 18. You don't need to measure it at every one of these things because unlike some of the more dedicated people, I'm not going to come in at midnight and do a measurement. I'll just make sure I'm there in the morning and do it. But one of the test questions they used to give over the years was, how long do you typically have to go for one of these things? And it can be up to about, is that right? 48 plus 6 is 54. Normally, like about 72 hours is what most people say you would have to do to get 30 microcuries. So basically, you take a measurement, so you should have, like 50 millicuries here, 25, 12.5, 6.25, 3.125, 1 point something, and then, down here you've got 30 microcuries. And if you plot these, you should get a line that's, a straight line. Whenever you measure it, so in other words, whatever times you measure, you should get a straight line that looks like this. Okay, so this is your predicted decay. And then when you actually measure it, okay, so at 6 hours, maybe it measures 92 millicuries. And then over here, 30 hours, how many half-lives is that?
5.
5 half-lives. So what should the activity be at 30 hours? If I have 100, so it'd be 50, 25, 12.5, 6.25, 3.125. So so maybe I've got like 4.0 millicuries here. And then down here I've got 29 microcuries. Okay, so remember, so long as it's within plus or minus 10%, we're good. Okay, but remember, this is my high area here. So high activity, how well does it measure high activity? Because again, you have problems with overloading the circuitry of your dose calibrator. If you have a lot of activity in there, it may not be able to count all of it. Or it may overcount it. But so long as it's within that plus or minus 10%, you're okay. A lot of times on these graphs, I've seen lines that represent the plus 10% and the minus 10%. So basically you just have to plot in here, and so long as it's in there, that's good. Usually if you do have more than a plus or minus 10% thing, you do have a couple of options. You can repair it, or try to repair it, but if not, so long as you have a correction factor for it, you're good. And so with your correction factor, if it's over 10%, then you can get away with this. So this is linearity. Does it kind of make sense? Everybody okay with it? Okay, and how often do you have to do this? That's the other thing.
6 months.
So 6 months.
So far, we're 0 for 2.
Every 3 months, right?
Every
Quarterly.
3 months, every quarter. Okay. And remember I told you, the state has a definition for a quarter. It says not less than 12, nor more than 14 weeks. I mean, most people would just say, okay, every 13 weeks. But the state, being the state, this is what their definition of a quarter is. So, and again, when these people from the state are coming out, this is what they're asking you to show them. All of your records for your dose calibrators and things like that, if you have them, okay? The rest of this handout talks about the gamma camera, and we're not going to worry about that yet. Okay, that's going to be our topic for next week. But what I would like to show you, and what I'm going to be sending you, these are some other things that you may want to take a look at when you get to the hospitals. Let's see here. Okay, this is kind of covers the rest of the radioactive material license, so we'll spend a little bit of time on that. But the personal training program, one of the things that I made sure that all of my affiliates did for the students was go through this with each student. Okay? So describe the radiation safety training required for all personnel who work with radioactive materials in the vicinity or areas where radioactive materials are used, stored. Include the form of training, frequency, duration, and subject matter. Did you guys get any kind of formal training when you went to the hospitals? Huh? Everyone down here is shaking their head no. How about up there in Fresno? Ashley, did you get any kind of orientation?
Of what, like seeing the department and stuff, or like?
Well, did they show you where the areas where the radioactive material was stored and used?
Actually, yeah.
And the potential hazards? They explained the potential hazards? The radiation safety?
Going into it.
Or they just say, this is where we have the radioactive material, don't hang out here. Don't take your breaks in this room. Okay, the pertinent California regulations, this also should have included an area, or telling you where the Title 17 is located. You all know where Title 17 is now, right? That's usually the first question they ask you. Okay, obligation to report unsafe conditions. Okay. Right to be informed of their radiation exposures and bioassay results. So when you're working with radiation, when the reports come in, you have the right to know what your radiation doses are. Okay, the posting of notices, regulations, copies of licenses, and license conditions. You guys should all know where the license is located. And when they talk about pertinent regulations, this is what we're going to take a quick look at here. Okay, prenatal radiation exposure. So if you become pregnant, one of my female students just told me that they were pregnant. So that's going to be interesting. And then the ALARA program. Okay, this first thing here, this is something you do every day. And this is one of the areas that people kind of get complacent. Okay, somewhere in your department or somewhere in your procedure manual, there should be something that says, how do you order the radioactive material? Okay? So describe the procedures for ordering and receiving radioactive materials. So essentially what you would say in your procedures is, every day we look at the requisitions for tomorrow's scan. At 4:30 p.m. we call in the doses to the radio pharmacy. They deliver them at such and such a time in the morning to a secure location. That is very important. If they say that they just drop them off in the emergency room, you're done. Okay? They have to be delivered to a secure location. Usually you'll have to say that the security guard escorts them and opens the door to the hot lab, and they put them in this area here, or blah, blah, blah. Okay, what do we do for off hours? Okay, they deliver it at 6 p.m., you come there at 8 a.m., so how much time do you have before you have to go through the verification, quality control, and all that other stuff?
Isn't it every time?
Well, I mean, how much time are you allowed legally? Okay. Good question, huh? Okay. 3 hours. Okay. So from the time it opens, you have 3 hours to make sure that everything is done. Okay, notifying persons upon receipt of radioactive materials. So in other words, what do you do, or who do you notify when there is, excessive readings or spill or anything like that, or something inappropriate? So that's what you have to specify, because let's say that you happen to be the first one there in your imaging center, and as you know, there's not a lot of technologists running around, is there? Some of your sites. You may have one person. So they get there late, and you have a package that looks like somebody crushed it. And there may be some wet stuff on there. Okay? So who do you notify? Okay, now, and now where would you find the information on where the RSO is located? And so when you guys come to a new training site, they tell you, hey, welcome to Kaiser, Montana. Okay, our radiation safety officer is John Radke. This is his phone number and extension. And if he is unavailable, here's the number for GE Pharmaceuticals. And here's their phone number if you detect anything wrong with the packaging. Otherwise, you get to sit there and babysit this radioactive package and probably get a lethal dose of radiation, in which case we will give you your certificate posthumously. Say, we would love to give Viat his certificate, but since he got an overdose of radiation, we will give it to his family in memory of him. You have to really be careful, you guys. Some of the stuff that they ship to your hospitals is pretty dangerous. You get a couple of 100 millicurie doses for therapy patients and things like that, you're going to get some pretty high radiation. Okay? But this thing should either be in a procedure manual, or most people post it on a wall. Hopefully outside the area where the radioactive material is. Does that make sense? Yeah, so you have like a bulletin board in some area where if there is a leak, and that whole area is contaminated, you don't have to spend 2 hours, reading it. Okay. Okay. Then the other thing is, okay. So that's. I'll take over here on the next page. Then it says, security personnel, whoever is going to be receiving the package shall have issued and written. They shall have been issued written instructions on procedures to follow. I don't know about your hospitals, but we change security guards more frequently than we change underwear. Okay? So that means we have an area that these guys have to look at and read before they escort the delivery guy back to nuclear medicine. Okay? Then moving along here. Okay, procedures for safely opening packages. Okay, this is something that you are required to have in your department.